Welcome to Easy Math TV. This is our final video in our series on RStats and the labs that we completed for this course. Our final lab is a simple linear regression, and again, we're going to be looking at our baseball data. And so the first thing that you're going to want to do uh, before you go any further with this video is I'm going to ask that you go ahead into your files for the lab and open up the HTML file that says simple regression.html, and open that up and just read through the entire thing all the way down to, where it says lab. It should say lab number 9. Lab number 9 ends here. So once you get to that point, just just kind of familiarize yourself with what the lab is about, and then come back to this video. Okay, so I'm going to move it over to the side. Since there are issues with Posit Cloud right now, I'm actually using RStudio, and I'm not sure. I may have to split this walkthrough into two parts again. It really just comes down to like just how much explanation I end up having to do. But again, I don't want to have to explain a lot of the concepts behind what we're doing. So let's just get right into the actual code itself. So I've made this accessible to you. Basically, the code file is interactiveregression.r. So I'm going to just open that up, and it appears in the upper left panel of our screen. So I'm using RStudio, which is this is the Posit Cloud for the desktop. Okay, so Posit is the company that that bought RStudio, and RStudio is the kind of the older term for it. But this is the desktop application that you see in front of you, and it looks very similar to Posit Cloud, so everything should pretty much work the same way. We still have our plots window down here in the lower right. We have our environment window in the upper right. We have our R code file in the upper left, and console in the lower left. So the console is is where you will see code get executed. Okay. All right. So let's just tear right in. The very first thing that we want to do is install a package. So library parenthesis statsr close parenthesis. If you haven't already installed that package, we need to. And like I actually ran into issues with that in Posit Cloud. So like if you do as well, I'm not going to force you to use it. There's only one thing that comes up further down. We're going to get to it in a moment, that you will not be able to do along with us. But you can certainly follow along with what I'm doing here. Okay. All right. So our first task is to just get our data. So let's load our data. And again, what I've done is I've created a simple random sample from the big data set that is our MLB players from 2018. We actually used that data set in class the other day to do some ANOVA, and we're using that same data set, but I created a simple random sample of 30 players from it so that we can do some simple plotting and see if we can do some regression. Okay, and see if it actually makes sense to do regression. So the very first question that you're going to be asked concerns, hey, do we even have a relationship between these variables here? And the two that we're most interested in is the at-bats. So let me just explain what we have. We have AB, which is at-bats. We have HR, which is home runs hit. And then we have capital R, which is runs scored. So when you are recruiting players, often we are most interested in how many runs they've actually scored. Everything else kind of goes hand in hand with that. But the big statistic that we are most interested in that actually leads to the success of a team is how many runs are actually scored by players and by the team. And the big question that we're going to be addressing with this lab is, can we predict what the runs scored would be if all we know is the at-bats? And then the same thing with the home runs. Can we also predict what the runs scored would be if all we know are the home runs that the player hit? You know what I mean? So A, is there a correlation between those two? B, is it linear? Is there a linear relationship or pattern between those two variables? And then C, can we actually create a prediction model that would help us to like plug in, say, a number of at-bats and then output a number of runs scored? Okay, so we're very much interested in that question. So before you answer any more questions, you are going to do these two lines here. You're going to run a correlation test, and then you're going to plot AB versus R. So on the x-axis is going to be our at-bats, and on the y-axis is going to be the runs scored. So let's hit run. In the console, we see our correlation coefficient, and that we can only use if we are convinced that there actually is a linear pattern between these dots, between the at-bats and the runs scored. So since this is one of the questions that I'm asking you to answer, I'm not going to answer it for you, but I will just point out, here's our plot. And your job is to decide whether or not you feel that there is a strong linear relationship. Do the dots seem to be flowing either up and to the right or down, or maybe they're going down as you go to the right? That would be a negative relationship. If they're going up to the right, that's a positive relationship. And do you feel that there is kind of a linear pattern here? So if you do, then you can go ahead and look at the correlation coefficient, which is the 0.9648787, and that tells you what the strength of that linear relationship is. So first, is there a linear relationship? And then secondly, what is the strength of that linear relationship? So now that you've made that plot, you can actually answer questions 1 and 2 before moving on to the next thing. So the next thing that we want to do is we want to actually put our data into a data frame. So I'm just going to hit sample data equals as.data.frame. And then inside there is a column it's going to make columns out of our data. And let's just hit that and run it. And so in my environment up in the upper right, you can see sample data has now appeared. Sample data has now appeared. So now this is the interactive part of this lab, and it's really a lot of fun. Hopefully you will manage to get that package installed, the Stats-R package, because if you don't, you will not be able to do this nice interactive exercise that's coming. So I'm just going to run through it a couple of times for you just to show you the basic idea. And it's basically plot underscore SS, so SS is for sum of squares, and we're plotting X versus Y using our sample data. So that's this line of code right here, and I'm going to hit run on that. So a new plot has just formed in the plot window, and the dots are just scrunched up a little bit more. And notice that there's now a directive for us in the console. The console is actually telling us to click 2 points to make a line. So my job is to just pick 2 points. So I'm just going to kind of pick the one that's all the way on the left and the one that's all the way on the right just to start with. So you know that you've done at least a decent job if there are a bunch of points above the line and a bunch of points below the line. That's what we want. We want to see kind of roughly half of the points above the line and roughly half the points below the line. But we don't want to necessarily have them be like all of the below are on the left and all of the above are on the right. We don't want to see that. Um, so this isn't exactly the best choice that we could have made. And you can actually see that over here in the console. In the console, we have the two numbers that we would need for the equation of that line are here as our coefficients. And the coefficients are your y-intercept and your slope. So by choosing those 2 points, basically I have a slope of 0.1345 and I have a y-intercept of 1.8651. But my sum of squares, this is the total error that I have. And that's pretty big, 2036.82. I think we could do a better job than that. So I'm going to go up here and I'm going to highlight that code again, the same line of code, and I'm going to hit run again. And it's going to give me another chance to choose another pair of points. So I don't know, let's go with this one here. And I don't know, maybe this one. So I don't know. I guess it's a little bit better. This one has a y-intercept of negative 17.4892, and it has a slope of 0.1925. And the sum of squares is a little bit better. It's 1,766.648. We want to get that number as small as we possibly can. So I'm going to run this one more time. And this time, let's see. I think I'm going to go with this point here. And maybe this point here. Oh, that's actually worse. So my y-intercept is negative 22.8897 and my slope is 0.2027, but I keep going in the wrong direction with my error. My error is 1973.681. Oh goodness. So for your purposes, you're going to want to keep doing this until you can perhaps find 2 points that will give us I don't know. We just need a better result here. I don't know what's going to help me out. I need to pick something a little better. So let me just pick that one and this one. Ooh. Okay. I think I'm going to stick with that as my final answer. My final answer is going to have a sum of squares, and you may actually manage to get better than mine. I don't know. But I'm going to challenge you to try to get a better sum of squares than 1,327.392. I did that here by selecting these 2 points that you see here with little tiny X's on them. And my y-intercept was negative 8.5277, and my slope is 0.1636. So that's basically what my best guess line is going to be. I'm going to try to zoom in on this because I want you to see something really carefully here. There are some dotted lines between the points and the line that I actually have identified. So those vertical little dotted lines are the residuals. So we have basically error. It's the error from the data point to the line. And so that we call those little e subscript I values. And because I is like an index, so the index goes from point 1 to point 2 to point 3 all the way up to point 30, you know. So the index is going to go from 1 to 30. And this is your error 1 and this is your error 2. So if the point from the data is above the line, the error value is going to be positive. If the point from the data is below the line, the error is going to be negative. So that's why we square them and we take the sum of those squares to get our sum of residuals, okay? So that's basically where that comes from. And so you get to do that multiple times. And then if you say show squares equals true in your directions, then you basically get, you're going to get something similar. So let's see, try this again. Okay. Ooh, wow. Wow, I even beat my last one. So now you're actually getting your not just the residuals, but the sum of squares of the errors. Those are marked on the graph too. It's hard to see, but you can zoom to see it. Okay. So once you kind of have played around with that a little bit, now you can answer question 3 before moving on. And I think I'm going to stop the video here, and then we're going to take up with part 2, and we're going to talk about actually how do we actually create our best fit line from our data, and how do we know that it is actually trustworthy or that we can actually use it to make predictions. So like, subscribe, comment down below, and I'll see you in part 2.